so now we're going to talk about Lagrange multipliers. Okay? So now, instead of talking about the critical points and setting their derivatives equal to 0 to find the maximum or the minimum, now we have a three-dimensional surface, f of x, y, z, and then we have a constraint, this g of x, y, z. So this is a surface intersecting basically another surface. And so we can't do our normal procedure of setting the partial derivatives equal to 0 and then checking the second derivative test. That doesn't work. Okay? But when you have this type of constraint. So what we're going to do is we're going to set the gradient of f equal to lambda times the gradient of g. And that lambda is what's known as our Lagrange multiplier. Okay? So let's just get started on the problem. We'll do this just as f of x, y over f of x, y, z. So let's say f of x, y is going to equal x squared plus y squared. My g of x, y is going to be x, y is going to equal 1. Okay. And so when I think about this problem, I think about, okay, so think about whenever we're in like linear algebra, if you're going to look for lambda associated with the matrix, you have a times b is going to equal lambda times b. That's looking for an eigenvalue. So what do? You take the determinant of a minus lambda I and you set it equal to 0. So what we're going to do is we're going to take the gradient of f minus lambda the gradient of g and set that equal to 0. Okay, so it's basically subtracting lambda gradient over lambda gradient of g over to the other side. So the problem that we want to solve is the gradient of f minus lambda times the gradient of g, and we're going to set that equal to 0. Okay, so just moving that lambda gradient of g to the other side. All right, so let's look for the gradient of f. The gradient of f would equal derivative of x squared would be 2x, and the derivative of y squared would be 2y. Okay? Now the gradient of g, okay, well the derivative of this guy with respect to x would be y, and y. Okay? Now the derivative of this guy with respect to y would be x. Okay? So the gradient of f minus lambda times the gradient of g would equal, this would be 2x minus lambda y and 2y minus lambda x. Okay. So this leads us to the equation 1, which is 2x minus lambda y is going to equal 0. And then we have equation 2. That's 2y minus lambda x equals 0. And then we have equation 3, which is the constraint that x, y has to equal 1. Okay. Now what you're going to do is you're going to take equation 1 and equation 2, and you're going to solve for lambda. Okay? So this means this guy would mean that lambda would equal 2x divided by y. Okay? And this guy would mean that lambda would equal 2y divided by x. Okay? So, from those two equations right here, now since we solve for lambda on both of these, what do? We're going to set them equal to each other. So, that would mean that 2x divided by y is going to equal now 2y divided by x. All right, so I can divide both sides of this by 2, get rid of the 2's, and then I can multiply both sides by x. I can just move that x over to this side, I can move that y over to this side, and what does this lead me to? X squared equals y squared. Okay? And then we can look at equation 3. Okay? X squared has to equal y squared. And x times y has to equal 1. Now think about this. You have the constraints based upon this is the constraint that has to be satisfied, okay? And this is looking for the satisfying the Lagrange multiplier, okay? So there are a lot of points in the xy plane that will satisfy the constraint and can be plugged into our f of xy, okay? So think about it. If you put 2 and 1/2, 2 times 1/2 is 1, okay? But 2 squared does not equal 1/2 squared. Okay, so it doesn't satisfy what we're looking for when coming to the Lagrange multiplier. Okay. So, what are the points that will really satisfy this? Okay, so only 2 points that will satisfy this: xy, which equals 1, 1. And xy, which will equal -1, -1. Okay? And now f of 1, 1 would equal 2, and f of -1, -1 will also equal 2. All right? So, then the question is, okay, we found these points. Are they maximums or minimums? Okay, so let's sample another point that will satisfy the constraint. It can be plugged into the problem, and let's see if it is larger or smaller than the point that we're dealing with. So I said 2 and 1/2 just a second ago. So 2 times 1/2 equals 1. It satisfies the constraint. Okay. And there's no reason you can't plug 2 and 1/2 into x squared plus y squared. Why not? So that's a point that is satisfying the constraint and can be plugged into our f of xy. So let's look at that one. So f of 2 and 1/2. Okay, so what does this become? That's going to be 2 squared plus 1/2 squared, which is 4 plus 1/4. Well, that's definitely bigger than 2. Okay? So this guy right here is a minimum. Actually, they're both minimums. Okay? All right. Let's try another one. I feel bad about using all this paper, but it is being recycled. Okay. So let's say and let's have a constraint that x squared plus y squared is going to equal 10. Okay, so try to think about what type of surface are we actually dealing with in this problem. Okay, so z equals 3x plus y. What is that? That's a plane. Okay, so we have this plane that, well, I know it's gonna, but if you have z minus 3x minus y equals 0, I know it passes through the origin. Okay, and so we have this plane that passes through the origin, it's tilted, and then we have the constraint that x squared plus y squared equals 10. So what is this? We're talking about a circle that is centered around the z-axis, and all, I mean, this is with a radius of the square root of 10, okay? So if I was going to talk about this type of surface right here, what would it be? I mean, the projection onto the y plane, xy plane, is going to be a circle that's going to be, if it's projected onto the xy plane, but then it's free in the z variable. So this is actually a cylinder, but not a filled-in cylinder. It's an empty cylinder, an infinitely thin cylinder. Okay, so what we have at this, for this problem is you have a plane and a cylinder, and so you're asking, well, given, let me draw a picture. So the picture is going to look something like this. So I got some type of plane. I know it passes through this way. And then we have some type of cylinder that's going upwards and downwards. And so where's it going to hit it? Well, it will hit the plane some type of weird angle if I extend the plane out further. Okay, that is a terrible picture. But you get kind of the idea. You have this plane, and then you have a cylinder. So you're asking, what are the maximum values of the intersection of a cylinder and a plane? Okay, so you can see just by this, second derivative, that's angle work. All right, so let's try to figure this out. So first, we're going to look at the gradient of f. That would be 3 and 1. And then we're going to look at the gradient of g. And that's going to be 2x and 2y. Okay? So, now we're going to look at the gradient of f minus lambda times the gradient of g. So this is going to be 3 minus lambda 2x and 1 minus lambda of 2y. Okay, so this is going to give us 3 equations. All right. So equation 1, we have 3 minus lambda 2x equals 0. Equation 2 is 1 minus lambda 2y equals 0. Okay? And then we have equation 3, which is the constraint. Okay? So these two equations come from the gradient of f minus lambda times the gradient of g, meaning that we're looking for the Lagrange multiplier. And the third equation is our constraint, meaning that it has to satisfy this property right here because that's the constraint, okay? So, now we're going to solve for lambda. So, this problem right here is going to lead to lambda is going to equal 3 divided by 2x. And this equation right here is going to be lambda, which is going to equal 1 divided by 2y. Okay? Now, once you've solved for lambda, then we can set these two equations equal to each other. So, from that, we're going to get that 3 divided by 2x is going to equal 1 divided by 2y. Okay? Now, if I multiply both sides by 2, the 2's will cancel out. And so what is this one going to lead to? The 3y is going to equal x. Okay, now that we've used the gradient of f minus lambda times the gradient of g, those two equations, and then solve for lambda and set those problems equal to each other. Now we're going to plug them into our equation 3, which is our constraint of the problem. Okay? So x equals 3y. So I'm going to plug 3y, we're at x right here. Okay. So that means that 3y squared plus y squared is going to equal 10. Okay. Well, let's clean that up a little bit. Right? So this means that 9y squared plus y squared equals 10, or that 10y squared equals 10. Okay. Well, if I divide by 10, I get that y squared is going to equal 1. Okay? So y is going to equal plus or minus 1. Okay. Now think about this equation that that's 3y equals x. Okay? So if y equals 1, x equals 3. If y equals negative 1, x equals negative 2. Okay, so we have 2 points, 3, 1, and negative 3, negative 1. Okay, so okay, now we have to ask ourselves the question, which one is a maximum and which one is a minimum? So instead of sampling points like I did on the other one, let's say f of xy equals 3x plus y. So f of 3, 1 would equal 9 plus 1, which is 10. And f of negative 3, negative 1, which would equal negative 10. Well, that's going to be the max, and that is going to be the min. Okay. Well, we got 20 minutes left. Let's do one more. This might be a long video, but yeah, oh well. Okay, so actually, we'll end the video